Now, members, we are going to see what happens if they ask for us to get errors in expressions. Expressions include formula for volumes, formula for areas, and so on. Now, so that means that you need to be good in this formula for given figures. So, the example is going to be from first principles, prove that the expression in percentage error in volume of a cone is given by this. Of course, they know that to get a percentage error, we need to get the relative error. To get the relative error, we need to get also first the error in the expression. But first of all, state the assumptions made. Now, we need also to get, first of all, to state the formula for getting the volume of a cone. So the formula for getting the volume of the cone is going to be given by a third, or some people say pi over 3, or can say pi r squared h. So this is the formula for getting the volume of a cone. Now, because we are dealing in errors, means that we are receiving a small change. And then the small change in radius is ER, and the small change is ER, then the small change in the height is EH. So if we get a small change in volume, it means that that was brought in by the effect of a small change in also the radius or the height, because the volume of the cone is variable with the radius and also height. So if the volume receives a small change, then we call it EB. It means that that was caused by a small change in radius. So there was an error in radius, which we call ER squared. Then also there was a small change in height, which I can say EH. As simple as that. Now, what we are going to do here is to expand this side. So now this one, this is going to give me now my V plus EV. It will be giving me a third pi into, can I expand this? AR squared into H plus EH, the error H. But so this one is very small, so you know that E squared R is very small, so it means it's going to approximate 0. So what we are going to do now, we are going to expand that thing there. So we have our V plus E V, sorry, this is in V equal to 2. So now, allow me, okay, we can leave it, but I wanted to write this one, the same. So this will give me now a third pi into, now let us, can I expand the space won't be enough. So I have now r squared plus 2r ER. From this one is approximately 0 into h plus EH. So now there we can expand as we want. So this will give us, now I'm going to take the other side. I'll be having a third pi into, this time this I get r squared h. Then this time this plus here and h, then plus. Now this time this 2r ER h, then plus ER EH, then times this 2r, then minus my v. And I take the other side. So you know that this one here is that our E, not that our ER times EH. These are very small, so if they multiply each other, they will approximate to 0. So we have now from here, my error in V equal to a third pi into r squared h plus r squared EH plus 2RH ER, this one, then this one I have seen is going to approximate 0. Then minus V. What is our V? Our V is here. So it's that our V is a third r squared h. So how are we to expand it? Okay. Or I can say, if I factorize out a third pi, our EV is going to be, if you factorize out a third pi, so here I'm bringing r squared h. Okay. Then I factorize out this, so this one means r squared h. And so at the all of this now is going to be smashed with that. So now, when we enter this, we have now our error in the volume as, so it's that we shall have this as pi over 3 into r squared e h plus 2 r h e r. So now this is the error in the volume. Now, if they want the percentage, to do that, we're going to get the relative error first. So, first of all, our relative error is going to be given by the error in the volume over the volume itself. So this would be, now we have this as third, pi a third into this is ER. Now we are dividing with the volume. Our volume is this. So we are dividing with pi over 3 r squared h. So it's that now this one is going to vanish with that. So now this one you can now so this is going to be now E. Okay, so I have EH r squared then plus 2 r h e r, the whole thing I'm dividing with r squared h. From here, I see that we can easily separate. This divides this and this divides this. So, our relative error is going to be now this. So, we have here r squared e h divided by this r squared h. Then plus this divides this and this also divides this. 2 r h e r divided by r squared h. So that this one is going to vanish. So 1 h goes, then 1 r goes with that. So this will give me now e h over h, then plus 2 e r over r. So now, if they want me to get sister, they want using math, so meaning they are getting the maximum relative error. So when I introduce also absolute signs inside our relative error, absolute to be now absolute this. Absolute, and we say this is less or equal to modulus of EH to ER over R. And now we say if this one is less or equal to this, it means that also this is going to be equal to that. So our relative error, if we want now the max, we shall take it as equaling to this. Allow me to start with this. So this would be now 2ER over R plus EH over H. Now, these two, we can easily remove these two out. So this will be 2ER over R, then plus EH over H. So now, if we're going to get a percentage error, now we said our percentage error is going to be the relative error. And it's 100. So this will be now, this is the relative error we got, which is 2 error in radius over the radius, then plus error in the height over the height. But remember, multiply this by 100, and that will be our percentage error. And so that's how we handle this question, and that's how we do it from past principles. Okay, so that's it, members. I wish you well. Maybe members, the other thing we are the state the assumptions. Assumptions means how did we come out to this formula? The assumptions we made are the error in radius and the error in height are very, very small, that their product will approximate to 0. Also, another assumption is that when you get the error in the radius and you square it, it also approximates to 0. So in simple terms, these are the assumptions made. Okay.